last class, the big idea that we covered was quantum numbers. We have 4 quantum numbers. I'm going to jump back to our recap slide for that, wherever it is. Here it is. Bonk. 4 quantum numbers. We have our principal quantum number. This is like our rings in our Bohr model. So our orbits, the tracks that our electrons sit on. We've got the angular momentum quantum number that's based on the principal quantum number. The options for our angular momentum quantum number are based on our principal quantum number. It equals 0 to n minus 1, whatever our n number is. And our angular momentum quantum number is also sometimes called a subshell, or I call it our shape family. So we've got different options for shapes that we can make with our orbitals, which are individual shapes where our electrons live. And our magnetic quantum number specifies which of those subshells, which of those shapes, those orbitals we're talking about. And this is equal to negative L to positive L, and it includes 0. And then our 4th quantum number that's not related to these other 3 exactly, it's not based on the other 3, m sub s, our spin quantum number, is equal to plus or minus 1/2. Plus for upspin, minus for downspin. So now with that little tiny bit of review, and hopefully what we remember from last time, we've got some sets of quantum numbers. Each quantum number set is supposed to specify one singular orbital, one singular shape. But each of these sets contains one quantum number that's not allowed. We want to replace the quantum number that's not allowed with one that is allowed, and I'm going to give us some time to work on that. All right, for our second practice round with quantum numbers, we want to be thinking about what options we can have, and these go in order. So for our n number, is our n number allowed? N equals 1, could be 2, could be 3, could be 4, and so on. Increasing, it starts at 1, though. Based on our n number is our L number, and our L number is 0 up to n minus 1. So for n equals 1, 0 to 1 minus 1, the only option for L is 0. For n equals 2, we can have 0, and we can also have 2 minus 1, which would be 1, so L equals 1. For n equals 3, L equals 3 is not allowed, because that would be n minus 1 would give us 2, which is the max or the biggest L that we could have. So we can't have L equals 3. Based on our m sub L, our m sub L, our magnetic quantum number, goes from negative L to positive L, and it includes 0. And so to fit a number in for our L here, we would have to have at least 2 for our L, because our m sub L is plus 2. N minus 1, 2 is the biggest L that we can have, and so L is what we should have here. So L equals 2 would fix that problem. For B, n equals 2, n equals 2, so L can be 0 up to 2 minus 1, so it could be 1. Our m sub L goes from negative L, negative 1, to positive 1. So it should be -1, 0, or +1 for our options. -2 is too big in the negative direction. -1, 0, or +1 would all be suitable magnetic quantum numbers. And then for C, we can have n equals 1, that's our lowest n number. Can we have L equals 1? With n equals 1? No, we can't. Because it goes from 0 to n minus 1. N equals 1, so L equals 0 to 1 minus 1, which is also 0. So L would have to be 0. And if L is 0, M sub L can be 0. So that number would be fine. And I'll just add in our last quantum number so that we have it again here. This is basically the block of things that you should have memorized. Those quantum number rules. Other stuff that you should have, L equals 0, 1, 2, or 3. These have letters that go with them, S, P, D, and F in that order. All right, moving on. For our atomic spectroscopy, those are the colored charts that we saw, the emission spectrum, where you had the slide and we had different colors in it. Might have looked something like that. We looked at those last time, emission spectra. We also looked at them in lab. So each wavelength in this atomic spectrum corresponds to an electron transition between orbitals. So we've got electrons moving between orbitals. This is the same idea as moving between orbits in our Bohr model. So we can have an electron that gains energy. So we've got a beam of light coming in and hitting this electron. That excites it. It goes up to the n equals 2 level. And then sometime later, in blue here, it relaxes. And to relax, it has to release some energy as light. You can also input the energy not as light, but as like electricity, which is what we were doing. So we were pumping electricity into our tube that had all of our stuff in it, our element in it. That excited it, and when it went back to its lower energy state, it had to release that energy, and it released it as light. Here's another way that we can look at that, where each of these levels is basically a different orbit in our Bohr model. So we've got an electron that's at the n equals 1 level. It absorbs some energy by electricity or some other method. That excites it. It jumps up to the n equals 3 level, and it'll be there for a little bit of time, depending on how stable it is. Eventually, though, it has to come down, and it drops, in this case, down to the n equals 2, and it emits a beam of light. Equal to the energy difference between n equals 3 and n equals 2 in this case. If it initially started at n equals 1, it would probably also at some point fall from n equals 2 to n equals 1 and release a different wavelength of light because the distance between 2 and 1 is different from 3 and 2. So to jump up to that higher energy state, it needs to gain the correct amount of energy that corresponds to that difference in energy. Electrons in those higher energy states are unstable. They're not going to be able to stay there forever. They're going to tend to lose energy, dropping down to a lower energy state, and they will release some light. And in our lab, we're working on predicting the emission spectra, checking how accurate we were for the emission spectrum of hydrogen. We can do this for hydrogen because it only has one electron. For reasons, we can only do it if the system has one electron, with some limitations on that. For an electron that's in the energy state n, one of those spots is occupied, and so it can jump to n minus 1 energy state. It's already in state, it can't jump to the same state that it's in. That would just be staying where you are. You can't say that I went somewhere over spring break and the place that you went is your house because you were there the whole time. It's not how it works. So this is a similar thing but for electrons. And so we can get n minus 1 lines. One energy state is already occupied. So n minus 1 destinations, places that it can go. To explain this, n minus 1. Both Bohr and quantum mechanical models can predict the lines for a one-electron system. If we look at this with calculations, the change in energy is equal to the final energy minus the initial energy, and this is just for hydrogen. So our final energy minus our initial energy. Last class we saw this calculation. We had this constant that was determined experimentally, and that energy was equal to 1 over the principal quantum number level squared. So in n equals 1, the energy of that state is just this number. If n is a higher value, then that makes this number smaller, and since it's negative, that means that it's closer to 0. So it's actually a bigger, or it's a more positive number, confusingly. What we can do with this, since they both have the same constant here, we can consolidate the constant up in the front, and so we put the 1 over nf squared and the 1 over ni squared next to each other. And I mentioned last class that we would see something that looks like the Rydberg equation, and this is it. We have a constant now in front instead of the Rydberg constant. This would be the Rydberg constant. And our NF is our final energy level, and Ni is our initial energy level. And we can do calculations with this. You can expect a calculation problem on the exam using this equation. Probably just one. I think I've only put one in the past, but we'll see. I think we do have an example problem coming up. So for our hydrogen energy transitions in radiation, n equals 1 is our lowest energy level. We also have n equals 2. Because of the energy difference between n equals 1 and n equals 2. Anytime we're jumping down to n equals 1, we're dealing with ultraviolet wavelengths. We can't see ultraviolet light, but it can burn us. But we can't see it. So even though some of those transitions are happening, we're not picking it up with our eyes. If you were looking at the lights for too long, they might have been hurting a little because of the UV light. Sort of like looking into the sun, but a little bit less intense. We can, however, see some of these lower energy transitions like n equals 5 to n equals 2. That would be our violet light. That's the biggest jump, and so it has the highest energy change. And violet, with a short wavelength, has high energy. So that's got the biggest jump distance. It's jumping the furthest. That corresponds to the most energy for visible light. Our green is from the n equals 4 to n equals 2, and our red was from the n equals 3 to n equals 2, because that's our lowest energy visible light. Do we have any questions so far about these transitions? Okay, which of these transitions is going to emit light with the shortest wavelength? All right, what do we notice about all of these transitions? They're going down. Which means that they would be emitting light. Because they're decreasing in energy, so that energy has to go somewhere and it's emitted as light. What else do we notice about the transitions? What's our change in n from 5 to 4? From 4 to 3? 1. From 3 to 2? Also 1. So they all have a delta n, a change in n of 1. So if they're all changing by 1 n value, how does our spacing change with our n levels? There's less space the higher up you go. So the higher you get in these n levels, the closer those levels get together. It's like if this is our, going back to our Bohr model, that's our 1, that would be our 2, that might be our 3, and then our 4 could be something like that. N levels get closer as n increases. We want the shortest wavelength. What is the shortest wavelength going to mean for the light? Is it high energy or low energy? Shortest wavelength will be highest energy. So for the highest energy, do we want the biggest distance or do we want the smallest distance? We want the biggest distance, because the bigger the distance, the bigger the energy. And since they get closer as the numbers get higher, 5 to 4 is going to be the smallest jump, 4 to 3 will be the next biggest jump, and 3 to 2 will be our biggest of the jumps, since they're all changing by 1 n level. So there's a lot of concepts that you have to know to be able to solve this problem. Or you just guess one of the A or C and you've got a 50-50. Questions about any of those concepts? You could also do it with a calculation if you use this delta E equation. And up next, we've got a calculation with that. So we want to determine the wavelength of light absorbed when an electron in a hydrogen atom makes a transition from an orbital where n equals 2 to n equals 7. And our equation is delta E equals negative 2.18 times 10 to the minus 18 joules, 1 over nf squared minus 1 over ni squared. Also delta E atom equals negative delta E photon, and lambda equals hc over E, where h is this, c is this, and it might also help. No, we don't need the, I'll put it there anyway, whatever. So this would all be information that you would gather potentially from your information sheet. All of these things you can expect on your information sheet. It might be a slightly different form. Probably the lambda and the E would be swapped here. So see if you can plug those in and get out the correct answer. All right, what values do we have that we can plug in? What information are we given?
H, C.
We're given H and C. What else were we given in the problem? N equals 2 and N equals 7. Where can we plug those in? Our NF and our NI. Which of these two is going to be our NF? 7 is going to be our NF, which means that our NI is going to be 2. The transition that we're making is from an orbital in which n equals 2. So from, meaning that that's where we're starting. To, which means that the next thing is our destination, or our final. So we're going from 2 to 7. And so we can plug in our 7 for NF squared and our 2 for NI squared. And then we can let our calculator do the rest. So our change in energy is going to be negative 2.18 times 10 to the minus 18 units of joules, 1 over 7 squared, which is 49. I'll write it as 7 squared and then make it 49, minus 1 over 2 squared, and 2 squared is 4. So we can put that into our calculator. You do need these parentheses, or you have to do the this 1 over NF squared minus 1 over NI squared separately. I think it'll screw up if you don't do that. And the value that we get out is 5.005 and some other stuff times 10 to the minus 19 joules. So this is the amount of energy that would have been absorbed by the electron to cause it to jump from 2 to 7. So the light must have been carrying this much energy. That was the energy of the photon, or energy of the light, and that's E in our lambda equals hc over E. So to calculate our wavelength, we plug in for H and also for C. And then we put our energy on the bottom. And we'll get something with units of meters, and it should end up being 3.97 times 10. 1, 2, 3, 4, 5, 6, 7, 10 to the minus 7 meters. And I think that's the same as 397 nanometers, because nano is 10 to the minus 9. Any confusions or places where we got lost or weren't sure what to do we'd like clarification on? The textbook should have other examples of this as well if you want to practice doing calculations. All right, we talked a little bit about this, and this squared is the probability density, which is the probability of finding an electron at a point in space. We're not really going to deal too much with our little pitchfork here. We'll just suffice to say that it's the probability over some volume. If you decide that chemistry is what you love and enjoy and want to do for maybe the rest of your life, and you go on and you take P-Chem, they'll talk a lot more about all of this stuff. Otherwise, I don't think it's really that important. So this is all just to talk about our s orbital. Our s orbital is when L equals 0. Our angular momentum quantum number equals 0. That is s. And within s, we've got some m sub L values. It's just 0, because it's from negative L to positive L, including 0. L is 0. Negative and positive 0 is the same as 0. So we're talking about our m sub L, which is our singular s orbital. We only have one s orbital because we only have one m sub L option. So we've only got one specific shape. That's what the orbitals are. We've only got one specific shape. Our probability density decreases as distance from the nucleus increases, so the further and further away that you get, the less likely it is that your electron is going to be there. And we've got plots of these, so we're going to look at shapes. Basically what we're saying with this is that it's like we're taking a billion pictures and showing you where the electron is likely to be. It's not actually moving around the nucleus. It's not actually orbiting like a planet around the sun in our solar system. My understanding is that basically the electrons just teleport. They can be anywhere in there, and we don't know where they are, but they're in there somewhere. So this is our plot. So we've got this vaguely spherical shape. So S conveniently stands for sphere, or we can think of it as standing for sphere. And what's confusing about this plot is that it looks like the electron is most likely to be found at the nucleus. But it cannot be at the nucleus because the nucleus is there. The electrons do not fall into the center, into the nucleus. So this is a little bit misleading if we look simply at probability density. We've got a graph here that's showing our probability density, how likely we are to find our electron at a given spot. The higher that we are on this plot, the more likely we are to find it there. And R here at the bottom is radius, so how far away from the nucleus are we? And it looks like we should find it at the nucleus most of the time. But that's false. And so we have a different function, the radial distribution function. The radial distribution function represents the total probability of finding the electron in a thin layer, so like taking cutouts of our little sphere, little tiny incremental pictures based on how far it is. And all that this does basically is fix our error from the previous slide. So this fixes the error in probability density So our probability density has a maximum at the nucleus that decreases with R. The volume of a thin shell is 0 at the nucleus. So when you're at the nucleus, there's no area there. There's no volume for that sphere because it's as small as it can be. The volume increases as you go further out. So we're multiplying how much area is there, how much volume is there, times the probability, and that fixes our error. And so instead we get the radial distribution function that looks something like this. So we've got our probability again on the y-axis. The further up we are, the more likely we are to find our electron there. And we've got the distance from the nucleus again as our x-axis. So we can see now this plot is 0 at the distance from the nucleus equals 0, and it increases up to a maximum at about 52.9 picometers, and then it drops off again. So what this graph is telling us is that we're most likely to find our electron at or around this 52.9 picometers. It might be a little bit outside of that, it might be a little bit inside of that, but most of the time it's going to be kind of in that layer. So it's sort of an orbit. It's not actually orbiting, but it's most likely to be found in that range. And nice for us, this is the same radius that Bohr had predicted, but conceptually they're different. So Bohr said that the electron is always at that distance because it's on that orbit track. So this is for Bohr. Bohr said that it was the electron just traveling around on that orbit. Quantum mechanics says it's most usually found, or most of the time it's found at that distance. If you had to bet, you would bet that it's at 52.9 picometers, but a lot of the time it's going to be outside, a lot of the time it'll be inside. And this is just for our 1s orbital. We also have 2s and 3s orbitals. 2s and 3s, because they're also s, are also spherical, but they're bigger because our n number has gone up. So bigger n means a larger shape. So our 1s is a small sphere, our 2s is a sphere that's bigger than our 1s, our 3s is a sphere that's bigger than our 2s. So these are larger in size, and they also contain a node. This is a point of 0 probability. So these include spots where we are never going to find the electron, or we would expect to never find the electron. And here's what they look like with little cutouts. So our 2s and our 3s, these white spots are where we do not find the electron. And we've also got our probability density and radial probability graphs, same idea as what we were looking at before. And we can see for our n equals 2 s orbital, we've got our node here where our probability is 0. For our 3s, we've got 2 nodes, and they show up here and here. I don't think I typically put questions about probability density or nodes. Nodes might show up, but probably not. Basically, the number of nodes just increases by 1 every n number you increase from your base, wherever it shows up the first time. I think the more important takeaway is that when our n number goes up, our sphere also gets bigger. So the shapes are bigger. So for our s orbital, each and every principal energy level, which quantum number symbol is that? Which one's our principal? M sub s, M sub l, L, or n? It's n. So each of our n levels has one s orbital, where L equals 0. This is always going to be our lowest energy orbital in any given n level. It's spherical because it's an s orbital. The number of nodes or rings where the probability is 0 is n minus 1. This is like we saw here. So for our 2s, n equals 2. 2 minus 1 gives us 1. So we've got 1 node. For n equals 3. 3 minus 1, we have the big ideas here are 1s is our lowest energy orbital. S is always our lowest energy orbital for a given n level. S means that it's spherical. And the nodes thing is maybe like a bonus, if you remember that. Any questions about our s orbitals or nodes? So S for sphere, it's always our lowest energy because it's our lowest angular momentum quantum number. Maybe is how you could remember it. We also have p orbitals. P orbitals are when L equals 1. Each principal energy state above n equals 1. So P first appears. Everything above n equals 1 has 3 p orbitals. P first shows up in n equals 2, since L equals 0 to n minus 1. So L becomes a possibility when n equals 2. So that's why it's above our first. And we've got m sub L values of -1, 0, or +1. This is why we have 3 orbitals. Values for magnetic quantum number, 3 orbitals, 3 individual shapes in our shape family of P. And each of these points in a different direction along an x-axis. They're 2-lobed. P for, does anyone want a peanut? They sort of look like a peanut. Or a dumbbell. All of these are going to have one node at the nucleus. So we'll have a point of 0 probability at the nucleus. Here's what our p orbitals look like. With our radial distribution function on the left side. Px is along the x-axis. Py is along the y-axis, here shown as the in and out axis. And Pz is along the z-axis, which is our up and down axis. We also have d orbitals. What's the first n number that d orbitals should be in? So every principal energy state above n equals 2, so starting at n equals 3, is going to have 5 d orbitals. We've got 5 options for m sub l, meaning that we've got 5 orbitals, meaning we've got 5 separate individual shapes. Look very similar. They're aligned just in different planes. The fifth one is goofy, and that's our dz squared. The subscripts will tell you what they mean or how you can remember them, but you don't need to know these ones. I would recommend knowing your p orbital labels. You don't have to know the match between the m sub l and the labels either. These are primarily 4-lobed orbitals, or 2-node orbitals. One node, our D has 2 nodes, our F has any guesses? It's 3. So 2 places where you can fruit ninja chop, and there's not going to be any electron density on that plane. That's all the nodes are. For D, I think of this as double dumbbell, which is also why I say that the p orbitals are double dumbbell. If you go to higher principal levels, for all of these, they're going to have extra nodes. Here's our d orbitals. So our double dumbbell shape, notice they're at 90 degrees to each other. For yz, it's in the plane that's formed by the y-axis and the z-axis, and they're off at 90 degrees. And so this would sort of be like doing an X shape with your body in the YZ plane. And if we switched it to the XZ plane, you just rotate 90 degrees. And I'm not going to show you the XY plane because that would involve me planking or getting on the ground, and I'm not going to do that today. So our XY is flat. It's in the XY plane. Our x squared minus y squared is along our x squared minus y squared, our lobes, what am I doing? Lobes point along x and y, rather than being between. And then dz squared has one that's on the z-axis plus the toroid, which is our math word for donut. For whatever reason, that's the shape that it has. Any questions about S, P, or D orbitals? Yes?
What's the first word in the middle one?
This word?
Yeah.
Lobes, the pointy parts. We also have f orbitals. We will look at the f orbitals, but be warned, they're scary. Our f orbitals show up for the first time in n equals 4. Each principal energy state above n equals 3 has 7 f orbitals because we have 7 options for m sub L. And we double the number of lobes that we have again. So now we've got 8 lobes because they've got 3 nodes. And a nodes is cutting it in half, so that's why it's doubling the number of lobes. Some of these are 2-lobed with a donut, a toroid. I think that should be 4-lobed. I don't think, maybe it's double toroid. We'll see. We're just going to look at them. You don't have to recognize their shapes because they are like super weird, and their labels are also uncomfy. I don't like them. And you can also have spherical nodes. So that would be like if you took your s orbital and you just took like the outer shell of your s, that would like chop through all of your lobes. It would potentially chop through your toroids or your donuts as well. Here's what our f orbitals look like. So we've got the ones with the double donuts on top, and then we've got our 8-lobed ones down below. Are those awful? Isn't that the worst? And then if you look at the labels too, fz cubed minus 3/5 z r squared is just awful. The other ones are basically the same thing, just for different axes. F xyz, fy xz minus z squared, a different thing times the other things minus each other squared. What a mess. So that's what they look like. We're not going to do anything with them because it's kind of pointless, in my opinion, at this level. Okay, summarizing for our different orbitals. For our n level, 1, 2, 3, and 4, we've also got subshells and L values. Our 0, L equals 0, is what letter? What letter goes along with L equals 0? S, P, D, or F? S. We can also have 1, which is P. We can have 2, which is D. We can have 3, which is F. In n equals 1, we have just the S for our options. In n equals 2, we have 2 options. We've got S and P. In n equals 3, we've got 3 options. How many options do we have in n equals 4? If 1 has 1, and 2 has 2, and 3 has 3, how many does 4 have? It also has, yeah, it has 4. So S shows up for the first time in n equals 1, P shows up for the first time in n equals 2, D shows up for the first time in n equals 3, F shows up for the first time in n equals 4. And they show up in all of the higher n levels as well. So we see them for the first time in 1, 2, 3, and 4, but they'll still show up later on. So like n equals 5, I'll do it in a different color. 5 is also going to have all 4 of these. There's not like some secret 5th thing that we add in. So keep having those S, P, D, and F orbitals show up. I think that's a helpful way to remember where they show up for the first time You could also figure it out with your quantum number rules that I showed us previously and boxed in and wrote memorize next to. So these orbitals, these shapes that we looked at, these are determined from mathematical wave functions, which we sort of just hand waved away as like we're not going to look at it because it's too big and scary and complicated, which is true. A wave function can have positive or negative values, and it can also have a node where that wave function is equal to 0. The sign of the wave function, whether it's a positive or negative, is called its phase. We can have positive or a negative phase, and when orbitals interact, like an s orbital from one atom interacting with an s orbital of another one, they can be in phase if they're both positive, or they could be out of phase. They could also both be negative, I suppose. So this would be where one is positive and one is negative. If they have opposite signs, they're not going to get along and they're not going to bond. And we'll talk about bonding, I think, in like 2 chapters from now is when we'll start talking about that. We've got some better visuals, perhaps, for phases. So for our 1s orbital, it has 0 nodes. So it's all the same phase. For our 2p orbital, our first occurrence of the p orbital, we have 1 node. So half of it is positive phase, and the other half is negative phase. So we're representing the blue here as the positive phase, and the red here as the negative phase. We're not going to really look at d or f orbitals with respect to phase, so you don't have to worry about any of that. Questions at all about our quantum numbers? N, our principal quantum number, L, our angular momentum quantum number, m sub L, our magnetic quantum number, m sub S, our spin quantum number, any of our orbitals and what their shapes are S, spherical, P, peanut, D, double dumbbell, F, freaks. Okay, then we'll stop for the chapter there.